Cool. Okay, yeah, so thank you for the introduction. My name's Jacob, and today I'm going to be talking about Arches, a cycle-level simulator for exploring massively parallel ray tracing architectures. So just to start off, why do we care about simulating ray tracing architectures in general? And to answer that question, we want to be able to explore these new designs, and we want to be able to evaluate the performance of these designs, but we don't necessarily want to have to build actual chips or design actual circuits. That would take far too long, and it would be an unnecessary expense just to try to prove if a design works. And so instead, we simulate these. Now, with respect to ray tracing architectures specifically, we have a couple of unique challenges. And namely, those are the workloads are large, heterogeneous, and memory-bound. Large because we can have potentially millions of rays that compose a single frame. Heterogeneous because the origin and direction of those rays, along with the structure of the scene and the BVH, drastically impact the amount of compute and memory accesses done per ray. And memory-bound because, in general, we have plenty enough compute power to actually perform the intersection tests and do the traversal. And so we're really limited by how fast we can read node data into our cores. And because of these limitations, we kind of have to render an entire frame to glean useful insights. For instance, we can't just render part of the frame or a downsized frame, like a reduced resolution frame, because the number of rays in flight affects how much these memory reads are amortized over the course of an entire frame. So we're kind of stuck rendering full frames. And we also, for the same reason, are kind of stuck with rendering for simulating full chips. So again, the effect on the memory system and the cache hierarchy is dependent on the number of processors that are hammering on it, or the number of traversal cores that are hammering on it. And so to really capture the full performance of one of these systems, you have to simulate this entire chip. And oftentimes, we're talking about GPU-scale chips that are massively parallel, as the title says. And so these chips can be quite large. And what really all of this boils down to is that we need a simulator that is really fast. We need to be able to very quickly evaluate our simulations so that we can get useful results in and not spend days or hours or even days waiting for results. And this really gets at the shortcomings of existing simulators, specifically when trying to simulate ray tracing architectures. And that's namely that they're slow. So like I said, on traditional simulators, it's not uncommon for it to take hours or even days to simulate a single frame of ray tracing work. And really, we want to be able to simulate multiple frames because we want to not just look at one ray distribution, we want to look at different ray distributions, and we don't want to look at just one scene, we want to look at multiple scenes. And then the other one is that a lot of existing simulators are designed specifically to simulate a specific architecture, and that's not necessarily what we're interested in. We're interested in exploring new designs. So we need something that's very flexible and easy to create new architectures from, and that doesn't really exist in most existing simulators. And so just to take a step back, we can approach hardware simulation at sort of three different broad levels. The first would be a functional simulation. That's going to simulate the functionality of architecture, so like the end-to-end functionality. And ray tracing, that might just look at like something that simulates the actual traversal of a BVH, but not necessarily the individual hardware components involved in doing that. And then a step below that, we have cycle-level simulation. I kind of had a spoiler in the title slide. This is what we're doing. But cycle-level simulation models each individual component of the hardware, and it also models it at a per-cycle level, so we can get useful insights from it, like performance or power estimates. And also, we could go down to the logic level, and that would be simulating the individual gates and wires on the chip. And this is sort of it's a very complex way of simulating. It's necessary if you're building an actual architecture, but it's far too cumbersome and complicated for quick research iteration. And so that's why we go with cycle level. And then so to summarize, our goals with Arches is to create a cycle level simulator that's fast because we need to run large workloads, accurate because we want to make sure that our results are telling us something real, and easy to modify so we can test new designs, not just existing designs. Easy to debug because, as anyone who's worked on simulators will tell you, you spend most of your time debugging them. And we also needed to have detailed and flexible instrumentation because once we have this fast, accurate simulator, we want to be able to glean useful research information out of it. And so that brings me on to arches. So for arches, we started off with a modular design, and what that means is that we represent each component of the architecture as a separate module. So cores, shared functional units, caches, DRAM, each one would be represented by a different module. And this has the nice benefit that you can simply create new architectures by rearranging these modules. So say if you wanted to modify your memory hierarchy, you can insert a new level of cache just by adding a module and hooking them together. And these modules communicate through interconnection networks, so this is very similar to how actual chips work. And this gives us several benefits. The first is fair arbitration, so we get the same type of fair arbitration you'd see on a real processor. And it also provides a common interface for these modules to be agnostic to each other. So for instance, the L1 cache doesn't need to know that it's hooked up to an L2 cache. It just needs to know that there's a memory system capable of servicing requests that's above it, and that could be swapped out for a DRAM system or something else. And then this sort of second design decision we made with arches is to have this two-phase cycle. So we break each cycle into two phases that we call the receive phase and the send phase. And what this means is that on the receive phase, all modules gather their inputs, so other modules trying to send data to them, they collect it. And then on the send phase, they output their results, so they send their results to the next module. And what this allows us to do is trivially parallelize the system. So all the programmer has to remember is that you collect results on the receive phase and you send results on the send phase, and then the simulator will take care of things like multi-threading, and that allows us to gain performance in the actual simulation. Oh my God. Okay. Close your eyes. Yeah. So like I said, and that comes at very little overhead to the actual programmer, which was a big goal of ours. And so these are some of the modules we currently have implemented. So we have all the things you'd sort of expect: compute cores to execute assembly instructions, shared functional units for things like divides or transinitial functions that you don't want to have per core, but you want to have shared among multiple cores. We also have caches, so we have a very flexible cache model that we can use to simulate different hierarchies, SRAM for things like local scratchpad, and then we have a very detailed DRAM model that's actually the Ramulator model. So that's an open source DRAM model that we didn't write, but it's a very well-established and accurate DRAM model, which is really important for studying things like ray tracing, which are memory bound. And then we also have dedicated traversal cores, like you'd see on modern GPUs, that perform full hardware traversal. And then in addition to this, we have a bunch of other custom units that some are related to research, some are related to other things, but these are sort of the important ones. And then sort of going on to how we've actually implemented these modules, because it's not super useful for me to just tell you that they're compute cores. That can mean a lot of things. But specifically what we've implemented is these MIMD compute cores. So this is a little bit different than what we see on GPUs. Each thread has its own program counter and is capable of handling divergence. And then they're also multi-threaded, so they can do things like latency hiding if you want them to. And each of these cores implement the RISC-V ISA, so we have the integer, atomic, and floating point extensions currently implemented within the ISA. And the reason we chose RISC-V is that it's designed to be extended, and it has reserved opcode space for custom instructions. So this is really important if you're working on custom hardware. You need to be able to communicate with the fixed function hardware units from software, so we provide a way within the simulator to do just that. And we also are able to use the GCC RISC-V cross-compiler to target our simulated architectures, which means that writing kernels for your simulated architecture is as easy as writing C++ code. And furthermore, that code can be shared between fixed function hardware within the simulator and software running on the simulated architecture without having to duplicate things. So things like data structures and like traversal algorithms can be shared. And then it also has the added benefit that it makes debugging kernels really easy because you can just compile it for the CPU and run it, and you almost get a functional simulation out of just that. And so the next sort of very important component within Arches is the cache model. So we tried to make the cache model as flexible as possible. It's set associative multi-bank cache. It's non-blocking, has variable block size, sector size, variable latency, And we also support various right allocation and eviction policies, as well as prefetching. And also you can organize these caches in a way to produce partition memory systems like the ones you'd see on GPUs, and this is really essential for high bandwidth, high performance memory systems. Like I said before, we also integrate Ramulator as our DRAM model, and this is implemented as its own module, so it inherits all of the threading benefits that I mentioned earlier. Each controller can be simulated in parallel, so you can get some parallelism there. And this gives us reliable power and latency estimates for the DRAM system. Like I said, these DRAM systems are very complicated, and they're very essential for understanding how things perform in practice, because they're very sensitive to memory access patterns, and so we decided to integrate something that's reliable. And then, like I said before, we also integrated our own rate traversal cores, not unlike the ones you might see on a modern GPU. And we have the option to either use these fixed function cores, or we also have options for software traversal or hybrid traversal using just triangle intersectors and box intersectors, for example. And then another really important component is the data structures and algorithms, and for that we have our own ray tracing math library that can be cross-compiled to RISC-V and run in software, or also can obviously be compiled natively and is included by both the simulator and the kernels. So we have things in there for building uncompressed and compressed wide BVHs, as well as tree-lit BVHs, and we can also have multiple different primitive encodings, including DGF, which has been integrated with the simulator. And then we also have different ways of representing the traversal state, so different stack representations. And like I said at the beginning, all of this is kind of useless if we can't glean useful information from the simulator. So to that end, we've made the logging extremely configurable. With these systems, you have many cores, which means many caches and many compute units. And so it's nice to be able to aggregate those all into one place. And we provide an easy way of doing that within the simulator, as well as doing that temporally. So sometimes it's useful to look at statistics across an entire frame, but bottlenecks can sometimes change over the course of a single frame. So it's also useful to be able to, say, look at a 1,000 cycle increment, and the simulator, again, provides functionality to do that. And then once you have all this data, it's nice to be able to visualize it, so we also have some scripts for visualizing it, and I've just shown some graphs of the DRAM read and write bandwidth for rendering a frame. So we also wanted to evaluate the simulator to make sure that the way that we've modeled these things is reasonable. And for that, we've decided to compare against the NVIDIA RTX 2080 and also VulcanSim. So VulcanSim is really the most modern simulator that supports ray tracing hardware. And it was built on top of GPGPU Sim, which is a simulator that aims to simulate NVIDIA GPUs. And crucially, it also includes Turing configurations, so we're very easily able to configure it to simulate the 2080. And of course, we also had to configure our simulator to match the 2080. Our simulator, like I said at the beginning, was sort of designed to simulate all kinds of different architectures, and so we were able to reconfigure it to simulate a 2080. And to do this, a lot of this information is not publicly known. So for things like the DRAM and caches, we took a lot from the spec, but we also had to take some from the VulcanSim simulator, and then we took the BVH structure from VulcanSim, and we used our own traversal cores. And then for the test setup, we wanted to isolate the actual ray traversal workload. So we pre-generate all of our rays, and we pre-generate 3 different distributions. Primary rays, which are the camera rays, secondary rays, which is a single bounce of diffuse GI, and tertiary rays, which is the second bounce of diffuse GI. And our shading is trivial. It's just computing a hash function of the primitive, and that's so that, like I said, our compute architecture differs slightly from a GPU, so we wanted that to not be a limiting factor. And then we also wanted to test a couple of scenes. So we tested Crytek Sponza, which is sort of representative of a very small scene, Intel Sponza, which is sort of a medium-sized scene, and San Miguel, which is a large scene. And here are the results we got. So you can see that across the board, we we match very closely to actual NVIDIA hardware. So within 16%, I think is the worst case on San Miguel tertiary rays. You can see that, but we can see that across very different ray distributions and very different scenes, we still seem to correlate very well with real hardware. And then just as a note, we weren't able to run San Miguel on VulcanSim because the BVH is absolutely massive and it causes a crash if you try. And then the other thing that we were really been harping on here is that we want this thing to be fast. And so we tested both VulcanSim and Arches on a i9 13900K. And you can see we don't get perfect thread scaling, but overall, when running on all threads, we're 71 times faster than VulcanSim. And I think this is really important because it's the difference between taking hours to run a single scene and taking mere minutes. And that allows you to test more test cases, to iterate faster, and to actually get more useful information out of the simulator. And so just to conclude, today I presented Arches, a fast modular cycle level simulator that's been tested on various different ray tracing architectures. So I talked about the 2080, which we used for validating it, but we've also simulated many other research architectures that we've been working on within the simulator, and it's available open source on GitHub today. And then this QR code will take you to the product page. So, yep, that's it. If we have any questions or...
Yep. Thank you very much. Yes, I already see questions, so I will.
Yeah, nice talk. I noticed that the performance numbers of the simulator were reported in, I think, cycles. I'm curious if you could estimate, like, what is the rays per second rate of your simulated ray tracer compared to the, like...
Oh, sorry, these?
Yeah, so these are the simulated numbers. I mean, when it's running in the simulator, what is the effective rays per second?
What do you mean?
The whole thing... yeah, I just mean it's going to be way slower when it's running in simulation as opposed to running on actual hardware.
Yeah,
so
yeah.
How much slower is that?
Like, what's the slowdown? Well, we can look at slowdown from clocks per second. So, was it 19,000 clocks per second on a 2080? Is I think the actual clock rate's like 1.6. Don't quote me on that. 1.6 gigahertz. So it's like about a. Someone else do the math. It's
so there's still
like
room.
100,000x slowdown. Yeah.
Okay. Yeah. So there's still room to be faster.
Well. Yeah, you could build the thing.
Probably there always is. Do we have another question?
One question, how do you feed the simulator? So you execute those programs that generate those rays, or you read them like from external buffer?
Yeah, so the answer is you could do both. Like I said, we can just compile C++ code to RISC-V and run that RISC-V natively on the simulator. For these test cases, we implemented a kernel in Vulkan for VulcanSim. We implemented a kernel in DXR for the actual GPU, and we implemented our kernel in C++ for this. And so all of those kernels do is they just read rays straight out of a buffer, and then they trace them and compute a hash. So for these tests, we're reading them out of a buffer, but there's no reason you couldn't generate them in software running on the simulator. Yeah. Does that answer your question?
Yeah. And
so does your system also, well, you mentioned something about energy use of the components. Is that something that you also evaluate with the simulator? And does it, for example, throttle?
Sorry, what do you mean by throttle?
Well, if
like power throttling.
Yeah.
Yeah. So the short answer is no. The longer answer is that we have the infrastructure to do power estimates for DRAM and caches. It's a little bit difficult to get like statistics on caches. So it used to be that you could just run cacti and get like a decent power estimate for like what the dynamic access power and the static power of a given cache design is. Nowadays, like I think the smallest node size supported by cacti is like 25 nanometers, which yeah, I see some people laughing. So it's a little bit difficult to get estimates for that, but it is supported by the simulator, assuming you can get estimates for a given cache design. Yeah.
Can you comment on the thing that's limiting your scalability in the number of threads here?
Yeah, so this is sort of interesting. The main thing is that we have to synchronize twice per clock cycle to do the threading that I described. And this was actually something we spent a lot of time experimenting with. We tried a bunch of things. I think ultimately it's just the thread synchronization. So if you think about simulating 19,000 clocks per second, you're having to synchronize all threads on the CPU 40,000 times per second. And so I think that in this case, that becomes the bottleneck. You can imagine like on larger chips, this becomes less of a problem because the amount of time it takes to execute each clock cycle becomes slower. But on something the size of the, 2080 is 46 SMs. So something that size, we sort of run into this problem. It's not obvious what the scaling should be because the 13900K is it's not a homogeneous compute architecture, right? It's got performance cores and efficiency cores. So we wouldn't expect 32 times scaling exactly, but you're right to point out that this scaling is not perfect. Ultimately, it was a design decision between how easy it is to work within the simulator and how fast it is. So we want this thing to be fast, but it being fast isn't helpful if it takes forever to implement a module. And so the trade-off was we can keep the modules really simple. They just have, like I said, two phases, a receive phase and a send phase, and they run every cycle, so it's easy to reason about them. At the trade-off of we don't get perfect thread scaling, but we're still 71 times faster, so I think it was a worthwhile trade-off.
Yeah, so, and if there are any other questions, please, you can grab him probably afterwards, and we have to prepare for the next session, but please give him applause for the